Good morning, good afternoon, good evening. This talk is about methods for predicting berm heights at South African Intermittent Estuaries. My name is Untitled Theron. I'm from South Africa, from the University of Stellenbosch, which is near Cape Town. This talk is based on a paper which was published last year, the authors being an ex-student of mine, Zane Booysen, and myself. This was published in the Journal of Estuarine, Coastal and Shelf Science in 2020. So, as I said, this is about methods for predicting berm height at South African intermittent estuaries, notably in data-scarce environments. In other words, we were looking for methods that required little input data but still gave robust results. Why are we interested in berm height? Well, the closure, breaching, hydrodynamics and ecology of intermittently open-closed estuaries are strongly related to the berm height. In other words, how high waves build the sand barrier across the mouth during closure. The research presented in this talk addressed or attempted to address this critical question. So basically, I'm going to briefly talk about the estuaries we used, the selected estuaries and data that we collected and used, then the 4 methods we developed to predict berm height and show some of the results, and then I'll make some brief conclusions in general. So these are the 20 estuaries we selected along the South African coast. We tried to use as many estuaries as possible, but there was some basic information we needed, and we tried to cover as many different coastal regions as possible. Note, the South African coast is wave dominated and has a microtidal range of tides along the coast. So what are we talking about if we say berm crest height? Basically, we were looking for the berm crest saddle point. The image on the right there shows an example from the Sekwe estuary, the red line indicating that berm crest saddle point by the dashed red line. That's the lowest point along the berm. So we had some survey data of the estuaries, but that didn't provide enough information on berm crest elevations. And so we had to use the water levels recorded inside the estuaries. That was the main source of data on berm crest elevations. The example shown here is a graph showing the water level as recorded inside the estuary by means of the blue line, and the red line is the river inflow into the estuary. So you can see a breach event there. In other words, in mid-July, the water level starting on the left-hand side was increasing, and then following that large river inflow event kept on increasing until the estuary breached at that specific high point. Then it breached and the water level dropped dramatically, and afterwards the mouth was open, and you can clearly see the tidal influence on the water levels there, the normal sea tides, the effect of those inside the estuary. And then gradually the mouth started closing, and some weeks later there's no evidence of any tidal influence. The mouth is completely closed and the water level is starting to gradually increase again. So the peak water level at the time of breach was used as an estimate of the berm crest elevation. So this gave us a lot of data to work with from these 20 estuaries. This is a box plot showing the results for the data for all these estuaries, berm crest elevations above mean sea level. You can see quite a wide variety there, and this also allowed us then to determine the maximum berm crest elevation for each estuary. So the first method we developed was just based on determining relationships between berm crest and various coastal parameters. In the end, we used for this first method just the beach face slope, the sediment grain size, the 1-year return period wave height at 15-meter depth off the estuary, and the mean tidal range. So the 2 graphs here just show 2 of these parameters. So the first method then was quite simple to apply further. We developed a scoring system for the different parameters and also a weighting system, and in conjunction with the weighted scores, the scores being related to how well the parameter for a specific estuary correlated to the maximum berm crest elevation. And in using these different weighting systems, 4 different weighting systems, we tested these to see how well they could predict the maximum berm crest elevation. So the 2 best ones are shown here. So these are useful as a sort of a first estimate method, which is requires very little input data, just requires application of that scoring system and the weightings, the details of which are provided in the paper that's referenced at the end of this talk. Then we focused on calculating or simulating run-ups at the estuaries, because obviously that's a key process in determining or the building up the berm and determining the actual berm crest elevation. So this led to the second and third methods. So we calculated hourly wave run-ups based on time series of waves and tides at each estuary, some of them quite a number of years long in length, the time series. And these graphs here just show the relationship between the measured BMAX and the 98th percentile rank predicted wave run-up for 17 of the estuaries by means of 6 different run-up models. Based on the results from this study, we decided to use the Stockdon model further. So in terms of developing the second method, what we did here was to determine the exceedance probability distribution of predicted 2% wave run-ups at each estuary. And we had the BMAX values, that's the maximum crest elevation of each estuary. So we could read off, as in this case here, the BMAX value for this estuary was 2.71, which then corresponded with the exceedance probability of 0.11 or 11%, in other words, for this estuary. So the bar graph on the right shows then these corresponding exceedance probabilities for each of the estuaries, ranging from 1 to 15%, which corresponded with the BMAX values for those estuaries. The average of all of those being at the exceedance probability being at 5%. So that's the method we used, or the value we used in method 2 for predicting maximum berm height. In other words, using this relationship between BMAX and the 5% probability wave run-up. So this is the most robust method of the 4 I'm presenting here, but it's also quite onerous because it requires time series of waves and water levels or tides, and then predicting the run-ups on this hourly time series basis, and then determining from that the 5% exceedance probability value. But it gives quite good results and is quite robust. The third method is basically a simplification of the second method. So it also predicts maximum berm height based on calculation of wave run-up elevation, but in this case just using a specific scenario, which is the 2% exceedance probability wave height, the deep water wave height, plus the 50% exceedance probability of the peak wave period, combined with the mean high water spring elevation, and using the Stockdon model to predict the berm height basically. And it gives almost equally good results as the second method, but it's very easy to apply. You only basically need some statistics of your waves and the mean high water spring level, which is generally easily available from various sources, and that gives you straight a prediction of the BMAX value for an estuary. So this is the method we would generally recommend to use. It's quick and easy and has quite low input requirements. The fourth method I'm just very briefly going to describe. So this method was developed to predict berm height on a timescale of individual breaches. In other words, to predict the berm height between individual breaches. So this graph here just shows an example from the Mhlanga estuary applying this method. And so the blue line shows the recorded estuary water level, and the thick brown line begins then as soon as the estuary closes, and then it predicts each hourly time step how the berm grows. In conclusion, we investigated berm crest elevations at 20 intermittent estuaries along the wave-dominated microtidal coastline of South Africa. We tested and developed 4 suitable methods for prediction of berm heights. The first method is the berm crest height criteria method, which was developed to predict the maximum berm crest elevation based on wave height, beach face slope, sediment grain size, and tidal range. It is useful for providing first estimates of the maximum berm crest elevation. The second method determines the wave run-up elevations and the exceedance probability threshold associated with the maximum berm height. This method is the most robust, but it is the most onerous as well. The third method, we call the design parameter approach, uses the 2% exceedance wave height, the 50% exceedance probability wave period, and combined with mean high water spring tide elevation, and the Stockdon run-up method to predict a single 2% run-up value. It provides results almost as good as the second method, and it's very easy to use. It's got little or low input requirements, so this is the method we would generally recommend. The fourth method is a stepwise berm growth model for short-term berm growth during inlet closure to breach cycles. It's based on the overwash potential. It's useful to look in more detail at this berm growth, but it's also a bit more onerous to use. Overall, we can say that the hydrodynamic and morphological variability displayed by the selected South African temporary open-closed estuaries increases the robustness of the results, potentially making the findings relevant to intermittently open estuaries in other parts of the world. Thank you for your attention.